Right, hopefully you've gotten some distance in this. Right, if you're looking to find the line of best fit for this set of information, okay, again, you go to your applications, choose Data Matrix Editor, just edit your current one, enter the years in your X column, enter the corresponding inches in the Y column. Okay. Now what do? How would you find the line of best fit, Rick? Okay. The Calculate tab. Okay. The linear regression, LINREG. Good. Assign the columns that represent X, C1, and then the one that represents Y, which is C2. Okay. Store it into one of your equations. Again, what that allows you to do is evaluate it more easily. And so now you get your equation where let's call, in terms of y is equal to 2.6x plus 24 is the approximate fit. Now, is this a positive or negative correlation? Positive. Is it relatively consistent? What percentage is it of the real line? 99.6%, right? So whatever the correlation is, that's the percentage or how close it is to being accurate. So this is pretty accurate based on this data. The fewer points you have, I mean, again, if they're relatively consistent, you might get a high correlation. Right? Now, if we were to write this in terms of height and age, so let's say height was h, age was a, or even let's call it lowercase h. Okay, so this could also be represented in height as 2.6a plus 24 approximately. Okay, now, one of the terms that came up, and nobody asked me about it, so I'm assuming that you guys looked him up, was interpolation versus extrapolation. Okay, did you guys look those words up? Or did you just guess until you got the right one, 50-50 shot? Was what? No. So interpolation means that you test a point between the known values. Okay? And it's usually it's the known values of x. So if I wanted to use this equation to interpolate the height of a 12-year-old, okay, so any age that falls between 2 and 19, the limiting values on the given piece is interpolation. So if I wanted to estimate the height of a 12-year-old, that would be an example of interpolation. Okay, so if I did, let's say, h of 12, the height of a 12-year-old, and in your calculators, you can go to the home screen. How would you find the value, the height of a 12-year-old based on this equation? You guys remember how to evaluate? Since you've stored it as your function, Henry.
I was going to say, could you just plug in, well, like h equals 2.6 times 12 plus 24?
Okay, so on this is an approximation, right? Because the 2 point, there are digits after the 6. So this is just kind of an approximation, but you can use the exact answer by entering y1 of, and then just typing the letter or the number that you're evaluating. So because we stored this equation in the y1 editor, anytime we type y1 in function notation of 12 and hit enter, so now we would expect the average 12-year-old to be approximately 55.3 inches. Okay, so in this set of data right here, would it make sense, let's say this is the average height of a male in the US. Okay, would it make sense that the average 12-year-old could likely be 55 inches based on this? Yeah, it fits within that, right? And now, what if I asked you to extrapolate? Extrapolate means that you're going to test a point that falls outside the known values. Okay, so what if I asked you to extrapolate and find the height of a 30-year-old based on this model? How would you evaluate that on your calculator? It's pretty easy, right? You just plug in a 30 here. Okay, 102.3 approximately inches. Okay. Now, would that make sense? How tall is that in terms of feet? If we took that number and we divided by 12. And so, how likely is it that a 30-year-old is 8.5 feet? Pretty unlikely, right? So sometimes when you're dealing with these data manipulations, okay, this set of information is pretty consistent. Okay, so if, let's say there is a linear curve, meaning it's pretty straight from age 2 to age 19, but after 19, what's going to happen? It's going to flatten out a little bit, right? So if you take data that extends all the way through ages beyond 19, you're going to be dealing with a different type of graph or equation. So do be aware of that. Again, there are some things that using lines of regression can be very helpful on, but then there's other things, even within the same problem, like these two things. You can predict the average height, but you can't for kids up to that age, but once you get beyond that age, it doesn't necessarily make sense. So be careful with the data. It's not always going to fit whatever pattern you see for everything. All right, what would be the equation, the inequality equation that relates to this graph? This graph models y is less than or equal to 3. Does anybody disagree? No? Good. Okay, so why is it the less than? The shading falls where? Below the line. Why is it an equal to? Lauren? Solid line, perfect. And then the y equals 3 is your equation, so you'll model it from that. Okay, what if I took this? And what would be the equation or the inequality that's modeled by this example? Okay, see if you can identify it on your own really quickly. Hey, Rick, what would you get?
Y is greater than 2 or 3x plus 2.
All right, so if you look at this, the equation has to be a y-intercept of 2, which we have, a slope of up to over 3, so a rise of 2, a run of 3. Okay. So we have the right equation. Our line was dashed line, so that's going to be no equal to. And we're shading above, so we have a y is greater than. So good. Very nice. Okay, let's take a look at one last thing. And what would be the equation or the inequality for this sketch? And what's the equation of the line, Nick? Okay, so now you have the right idea as far as you're identifying x. Hey, what is the equation for this vertical line? Is it a function, first of all? No, so because it's not a function, it's not going to be of that form y equals mx plus b. So there's no y in our equation at all in this particular case. So what's the one variable that never changes? X. Okay. And the equation that we'd relate it to is x is equal to what is the x coordinate that never changes? 1, 2, 3, 4 in the negative direction. Okay, and now are we shading all the x's that are greater than -4 or less than -4? Greater than? Are we including -4 in our set? So is there a solid line at -4? No, so you're going to leave it just greater than. And so this would be the inequality to express that relationship. Are there questions about what's g of 5 going to be? 15, and you get that because g of 5 fits into this second function. So we evaluate 3 times 5, and that gives us our 15. Okay, what about g of 7? So here we're going to evaluate in our last function. So 5 times 7 plus 1 gives us 35 plus 1, or 36. And then finally, g of 0. 0 is less than or equal to 3. So when you substitute that in, you get 2 times 0 plus 1. So you get your overall value of 1. Okay, questions on any of those, the piecewise functions? Okay, meaning that you might have a different function based on whatever the variables were. All right, so this brings us to the last concept that I want to talk about in this section. Okay. And that